Okay, so we're gonna start ME 564 with this lecture. This is a class about heat transfer. I guess just to sort of maybe cover a little bit about what we're going to talk about. The coverage in this class is going to be very similar to what you probably had if you had an undergraduate heat transfer class. So at UW-Madison, that undergraduate heat transfer class would probably be ME 364. And we'll cover basically the same topics. We'll go kind of quite a bit more in depth in hopefully every one of the topics. So we'll sort of start from the same place, but we're going to go a little bit farther. So some of what we talk about is probably going to be reviewed to you if you've had an undergraduate heat transfer class, and that's okay. I don't really know where everybody comes into the class starting from, so it's I think probably better for me to maybe be a little boring sometimes than to be a lot confusing a lot of the time. So we're gonna we're gonna go through some things that hopefully you already know, but we're gonna try to go a little bit farther. And we're going to focus on a few things. We're going to focus on solution techniques, some of which you've seen before. So analytical techniques, how do you solve ODEs? How do you solve partial differential equations, which might be new? Numerical techniques, which again, you may or may not have seen before. These are really useful techniques for heat transfer, for sure. But they're actually useful across sort of all disciplines of engineering, right? So, hopefully you can take some of what you learn here and apply it to other areas. Now we're going to use computer tools kind of a lot. We're going to use ease. We'll use MATLAB and we'll use Maple. So you'll need to make sure you have access to those tools, if possible. Maybe right away go get those. There's some tutorials that would get you started on ease if you've never used it before. We'll basically talk about everything you need to know in order to use Maple, and MATLAB is essentially a programming language the way we're going to use it, so there's not a whole lot to learn about using MATLAB. And again, these are also sort of generally useful skills or generally useful sets of knowledge that you can apply not only to heat transfer, but to other things. And then the third thing that I'm going to try to do is hopefully impart to you some kind of a conceptual understanding of heat transfer, right? So there's two parts to heat transfer. A lot of the time it seems like, we learn a technique and then we apply a technique and, it's kind of a cookie cutter thing. And then you go out into the real world and you find out that no problem you ever work on is quite that nice, that it comes in a cookie cutter format, right? You're not working in the lab and a problem comes up to you and says, remember that stuff you learned in chapter 7, that's what you need to do now. So part of being a good engineer is learning what is important and what can be neglected in a heat transfer problem. And that's really a lot of the upfront skill that's required in order to basically just be smart and make smart decisions. And then when you do analyses, do the right analyses, right? And that's really hard to teach, but it's really important. And so hopefully, as we go through this class, you'll be focusing on the tools that are required in order to make those kind of upfront judgments. What's important, what's not important, and then keeping what's important, how do I analyze the problem. So I'm not going to talk about the structure of the class because it might change from this semester to next semester, and I'd like this video to not have to be changed all the time. That's going to be laid out in a document, the syllabus, and you can look at that. So we're going to dive right into heat transfer. So we got to remember from thermodynamics what heat really meant. So in thermodynamics, we did all these energy balances. And, we would over and over again write down in equals out plus stored because energy is conserved. So whatever goes in either has to leave or it has to be stored. And heat came up when we were talking about how energy can get in, right? So first of all, heat is only relevant when you have a system with a control surface, and you're talking about how can energy transfer across a control surface. And there was different ways. One of those ways was heat, right? And heat was the transfer of energy due to a temperature gradient. And in thermodynamics, that's just what it was. It was this magic quantity which you couldn't calculate based on first principles. You were either given it or you were told it didn't exist, right? A boundary might be adiabatic. But, you sort of had to wait until this class, heat transfer, to be able to actually calculate what heat might cross a boundary given the physical situation. So there's two different mechanisms of heat transfer. There's conduction and there's radiation. There's what sometimes we call a third mechanism, which is convection. It's not really a separate mechanism of heat transfer. It's just a much more complicated situation where you have conduction, but you have it in a situation where the material happens to be moving around. It's a fluid, and so you have energy transfer due to the fluid motion, and everything just really gets kind of a lot more complicated, right? So in terms of topics anyway, we're going to cover conduction, radiation, and convection, which is probably exactly what you covered in your undergraduate heat transfer. So we're going to start with conduction, and we're going to spend kind of a lot of time on conduction. Conduction fundamentally is, is the energy transfer that is related to the interaction of microscale energy carriers within a material. So conduction happens inside of a material, right? It can happen inside of a solid or a fluid or a gas, but there's a material, and that material is made up of some kind of structure, and that structure has inherent to it, it has some energy carriers, right? And depending what the material is, those energy carriers can be different. If it's a gas, the energy carriers might be the gas molecules. If it's a solid, the energy carriers might be electrons, or they might be lattice vibrations, right? Whatever they are, though, they're very small. They're microscopic, right? Microscale energy carriers. And when those energy carriers get hot, they're moving around very quickly. And those hot, fast-moving energy carriers tend to collide with the cold, slow-moving energy carriers, and those collisions transfer energy from hot to cold. And that's the underlying basis of conduction. You have fast-moving energy carriers associated with high temperature, and they tend to collide and impart energy to slow-moving energy carriers at low temperature. To me, that's a very easy thing to visualize compared to radiation, which I struggle a little with sometimes, having a good mental image of. Conduction, to me, is just a natural kind of a thing to understand. So when we have a conduction problem, we immediately trot out Fourier's law as the rate equation, right? In 364 in your undergraduate heat transfer class, you probably use Fourier's law all the time, right? You have conduction, you bring out Fourier's law, right? We never really talk too much about, what it is and where it comes from and when maybe it stops being the right rate equation. So here's Fourier's law. It basically says that the rate of heat transfer per unit area, so that's what the double prime means, right? So this is Q dot double prime. This is a heat flux. This is watts per meter squared, the rate of heat transfer per unit area in the x direction, so the subscript here means in some direction, is equal to minus K, the thermal conductivity, times the temperature gradient in that direction, right? So this is a rate equation giving you the heat flux, watts per meters squared, in terms of what the temperature is doing. That's what all rate equations do, is they relate a heat transfer rate to something about the temperature. So here we have watts per meter squared. Over here we have Kelvin per meter. And then the thermal conductivity is this material property that must have units of watts per meter Kelvin. That's Fourier's law, right? It's directional. This is saying this is the rate of heat transfer in some direction, and this is the temperature gradient in the same direction. So, in three-dimensional space, I would have three statements of Fourier's law, one for every direction. Right? So that's Fourier's law, and I guess what I'd like to do today, before we just dive into using it over and over again in this class, is think a little bit about where it comes from, and like I said, when it stops being valid. So let's imagine a material, and here's the temperature distribution in that material, right? So here's temperature as a function of position. And you can see the temperature is not constant, right? The temperature is dropping as we move in the x direction, right? According to Fourier's law, here we have minus k dt dx, right? In this particular situation, if dt dx is negative, the minus k dt dx is positive. That says that we're going to have a positive conduction heat transfer in the x direction. Makes perfect sense to me, right? I'm going to be transferring energy from hot to cold. That's positive heat transfer rate, okay? So where does this come from? Well, fundamentally at the micro level, it comes from the motion and the collisions of these underlying microscale energy carriers, right? We don't tend to think of it at the micro level because we're engineers and we tend to work up at the continuum level. But if you were a physicist or a material scientist, that's all you would think about is what's going on at the micro level. So if I define a plane in this surface, so here's a plane at position X, I'm going to have some energy transfer through this plane. And what does that energy transfer arise from? Well, it arises from the fact that I have energy carriers moving through the plane from left to right, and I have energy carriers moving through the plane from right to left. And because over here on the left side of this plane we have high temperature, and over here on the right side of this plane we have lower temperature, those energy carriers moving from left to right tend to have higher energy than the ones moving from right to left, right? That is fundamentally what's going on to give me a net energy transfer through this plane. If the temperature was constant, if it didn't change, then I would definitely have energy carriers moving from left to right. I would also have energy carriers moving from right to left, right? They didn't stop moving around, but there'd be no difference in their energy because they come from a place that has the same temperature, right? So it's this temperature difference that's giving those energy carriers a different amount of energy depending on where they came from. Right? And that's what we're going to do next, right? We're going to think about what is the rate of energy transfer through this plane going from left to right. We'll call that Q dot X plus. This is related to energy carriers, crossing the plane in this direction. And then what is the rate of energy transfer moving from right to left? We'll call that Q dot X minus. That's related to the energy carriers moving in the other direction. All right, so let's focus on one of these terms. First, let's focus on Q dot X plus. So Q dot X plus at the microscopic level is related to what is the number of energy carriers per second crossing the plane in the positive X direction, and then you need to multiply that by what is the energy that each carrier has, right? So number of carriers per second multiplied by energy per carrier, I get energy per second, watts. That's exactly what I'm looking for, right? So let's break this down even farther. If I want to know the number of energy carriers per second crossing the plane, the first thing I would want to know is what's the number density of the energy carriers in the material? So what's the number of carriers per volume? What's the area of the plane, and then what's the velocity that those energy carriers have, right? If I multiply these three things together, so this is number of carriers per meters cubed times meters squared times meters per second, I get exactly what I'm looking for, number of energy carriers per second, right? Obviously, this isn't exactly right because the carriers are moving in not all one direction, right? So there'd be some geometry involved, but at least it's proportional to these quantities. What's the number density of the energy carriers? What's the area of the plane? And then on average, what's the velocity that these energy carriers tend to have? And then if we look at the second term, energy per carrier, well, the energy per carrier is just what's the heat capacity of each energy carrier, and then what's the temperature that the energy carrier has as it crosses that plane, right? So in terms of symbols, I have here that Q dot X in the positive direction is the number density, so N, little n, and then this ms just means microscale, right? So this is the number density of the energy carriers. The area, V with a little squiggle on it is the velocity, so this is the velocity of the energy carriers. C is the heat capacity, and then T is the temperature, right? So this is just taking this equation here and writing it again in terms of these symbols, right? and I'm carefully not restricting myself to a certain kind of material, right? These are just energy carriers, generally speaking, right? It doesn't matter if it's a gas or a solid, right? This equation is going to be the same. We're just going to be talking about different microscale energy carriers here. So the thing to look at next then is this temperature. So this temperature is the temperature at which my energy carrier experienced its last collision, right? So this is the temperature at X minus LMS, right? So these energy carriers are moving from left to right. This energy carrier crossing this plane right here, it came from someplace over to the left of the plane where it experienced its last collision with some other energy carrier. And that distance between collisions is given the symbol LMS. It's the distance it's the distance that an energy carrier travels on average before it experiences another collision, right? So these energy carriers coming from the left side, they experienced their last collision somewhere over here, and that distance is LMS. So this is T at X equals X minus LMS. If I do the same thing for the energy carriers moving from right to left, right, I'm going to have all the same terms here. The only difference is that those guys experienced their last collision somewhere over to the right of this plane, right? And that distance is also LMS, so this would be T at X equals X plus LMS, right? So I have two fluxes of energy then. I have this flux of energy related to stuff moving from left to right. I have this flux of energy related to stuff moving from right to left, right? They're not exactly the same, at least if the temperature on the two sides of the plane are different, these two fluxes will be different. And that's what gives me a net flux. When I talk about heat transfer through this plane, I'm talking about a net amount of heat transfer, not a gross amount going in either direction. Right? So if I want the net heat transfer through the plane, all I got to do is subtract the stuff going from right to left from the stuff going from left to right. I'm going to subtract the stuff going in the negative x direction from the stuff going in the positive x direction. And that's going to give me Q dot, which is the net rate of heat transfer, right? And so that's what I did. I took these two equations that we derived, I subtracted them. You can see that the number density, area, the velocity, and the specific heat capacity of the carriers, those are the same in both equations. So I pull them out, and really what I'm getting here then is just the temperature differences, right? So this is T at X minus LMS, and this is T at X plus LMS, right? So this is the equation that I get right here, fundamentally, if I look at what's going on at the microscopic level. This is the equation that I get and I use in heat transfer over and over again that has to do with looking at things at a continuum level, right? This is Fourier's law. These two equations don't really look very much alike, right? But somehow Fourier's law must come out of this equation because we know that Fourier's law is representing this phenomena, right? Fourier's law is our representation of what's actually going on at the microscale level. So the next thing we got to do is understand, how do I make this equation here look more like Fourier's law, right? So that I can understand, first of all, what assumptions go into that, so when does it break down, and then also what parameters give me thermal conductivity. What does thermal conductivity really represent, right? So that's the next thing that we're going to do.